All right, so I drew a molecule here, and what we're going to try to do is identify the major IR frequencies we'd expect from this molecule. So identifying everything that's possible as far as IR stretches. So every single type of function group possible here. So we can start to the left, I guess, move our way to the right. So on the left, you should see, right, this is a carboxylic acid. So what kind of stretches does a carboxylic acid have? There's two major ones I would look for. There's the OH part of it, right? So we'll say there's an OH, but it's a carboxylic acid OH. So it's a little different. Right? So remember the carboxylic acid OH is a little more jagged. You saw some of those maybe. There's a little more jagged. If you go back and look at our PowerPoints, there's some examples of all these functional groups are in there. So maybe a little more jagged. What else from the carboxylic acid will we have? The C-double bond O. Good. Right, that carbonyl stretch. And where is that carbonyl stretch at for the carboxylic acid? Carboxylic acid C-double bond O. So it should be in the carbonyl region, which is around 1700. So what's the specific stretch for carboxylic acid?
Oh, wait.
Carboxylic acid C-double bond O. So carboxylic acid, it just says acid C-double bond O, is 1700 to 1725. But now we're going to think a little bit and realize, oh, resonance could take place here with this carboxylic acid. And what in this case, what's that resonance going to do to the carboxylic acid stretch? Is it going to make it longer or shorter? Longer. It's going to give it more single bond character, right? In this case, resonance is going to move here and move up here. It's going to give it more single bond character, right? I'll draw the resonance structure after this. So we're going to expect it to be a little bit less than 1700 then, right? So we'll write less than 1700. That's where it normally is at. Right, these were 35, 32, I think. Remember, we know OHs are big and broad. What other stretches are there in this molecule? Alkene. So be careful. When you say alkene, let's as we move from left to right, this is an aromatic ring, right? Aromatic ring has a specific type of alkenes that's in your tables, right? So the aromatic rings have two stretches, 1600 and 1500 wave numbers. Right? That's more than just a C-double bond C. This is more a specific type. That's an aromatic ring. So it has those two stretches. What other things are on this aromatic ring? Alkene CHs or aromatic CHs, right? So we got to include those as well. So maybe I'll put that there, move that up. So we're going to say, I would like to say Sp3 Chs. What was the frequency for those? 3010
to 3040.
3010 to 3040, right? Yep.
And where are these?
Sp3 Chs. So these are Sp3 Chs, right? They're also aromatic CHs, you could say the same. Aromatic CHs are Sp3 CHs, right? These are Sp2 hybridized carbons.
You have a C-double bond to a
Now I have a C-double bond C, and that's what kind of C-double bond C is that? So right, C-double bond C. So sometimes it's helpful to draw on our hydrogens. What kind of alkene is this? So it's a C-double bond C. No, it's di-substituted, right? There's two hydrogens have been replaced, so it's di-substituted, and it's trans. So there's a C trans stretch, and where's that at? That's down the fingerprint region. What is that at? 960. All right. So that's like the bend of the trans. Where's the actual CC stretch at? Just a normal CC stretch. Where is that at?
1620 to 1680.
So you also have a 1620 to 1680. Now, that might overlap, right, with with this one as well, but you're expecting possibly it to be there. The one that's going to be really indicative that you really want to look for is this one, this trans one. That's really going to tell you what type of alkene. This tells you there is an alkene. This tells you, is it cis, trans, mono, di, tri, terminal, all those things. That's this number down here. And that one's part that one of those tables, 13.7 table, I believe it is. Be looking for that, which you'll be given. All right, I see one more functional group left that we haven't talked about. There's sp3 Chs. All right, don't forget out here. There's 3 sp3 Chs. So sp3 CH, and where are those at? Always less than 3,000 though. They're never above, so 2960 to 2850, but never above 3,000. Never above 3,000. If there's something above 3,000, it's not only an sp3 CH. It might be probably sp2. Good. So that's why I would attack this, and then I would go looking for the spectrum for all these things, right? And we've been practicing this a lot, and we're gonna add this. The biggest thing is you start to recognize these things, and looking at multiple choice questions or eliminate possibility answers, right? So I would if I was looking for this thing, I'd first look for the OH. If I don't see an OH, that isn't it, right? And then I look, are there sp2 CHs? And if there are, okay, then you start looking for the type of alkene, right? But the OHs and the NHs are pretty easy to pick out. Those are usually pretty strong, broad stretches. And then I look for the CHs, right? Because if there's anything past 3,000, I know it's not just an sp3 CH. So when you're given ranges, like 1620 to 1680, that means the peak will be around, it'll be in that range, most likely. It won't necessarily be as broad as that range, but it'll be in that range. Yep. All right, so let's say you have these two molecules. You have 4 trans octene. This is 4 trans, right? The H's are on opposite sides. Octene, 1, 2, 3, 4, 5, 6, 7, 8, oct. Ene as an alkene, 4. Where's the pi bond start? 4 to 5. 4 trans, 4 octene. The other one is hexadiene. 1, 5 hexadiene. 4, 5, 6. Hexa, meaning 6 carbons. 1, 2, 3, 4, 5, 6. Diene, 2 alkenes. 1, 5, meaning starts at carbon 1 to carbon 2. 5 to carbon 6. How do we tell these two apart? This is tough, because what kind of functional groups do both of them have? Essentially, they have the same functional groups, right? Almost the same. They both have, I would say, sp3 CHs, right? Both have sp3 CHs. They both have sp2 CHs too, right? There's an sp2 CH. There's an sp2 CH. Right, and same with the other side. They both have CC double bond stretches, right? They're both alkenes. They both have, right, CC double bond stretches. But are those double bonds the same? No. This one is a trans alkene. This is that fingerprint region. Where's the trans alkene at in the fingerprint region? 960?
Yeah.
Now, what are both of these? What kind of alkenes are these? What's the substitution on them? Mono, di, tri, tetra.
No, try.
So be careful. It refers to how many hydrogens have been replaced. So how many hydrogens have been replaced here? 1. So then it'd be mono. Mono, and then if two H's are on the same carbon at the end, we call that terminal. Right? 2 H's on the same carbon at the end, terminal. So it's monoterminal. Monosubstituted terminal alkene, what's the number for those? 990 and 910. So if you look at the spectrum, you might be confused, because you might be like, well, there's a big peak at 990, which is pretty darn close to 960, but then you should also see a big peak at 910 for this as well. And if you look at a spectrum, you really should see the 2 strong peaks, right? So that's the key. It's not just, right, everything's pretty much the same except for the type of alkene for each. So this question shows all these molecules, actually names them, but we should be able to draw them out. And the question is, which are IR active? So we talked about this very briefly in class. So basically the question is they had to be polar. They had to have some sort of dipole, right? Reason to kind of shake and bend. So what you want to look for is things that are really symmetrical, but without polar bonds are ones that will be IR inactive. Actually, it's asking, sorry. It should be active, right? So the same way is look for ones that are inactive. So you want to look for things that don't have polar bonds and are symmetrical. So no polar bonds. And symmetrical, like no polar bonds and symmetrical. So let's go through these. Let's do acetone first. Does acetone have polar bonds?
Yeah.
So is it going to be IR active?
Yeah.
Yes. Does this 2-methyl-1 or 2-methyl-2-chloro-propane have polar bonds?
Yeah.
Yep. Now we're down to these other guys. So here, here, and here. Do any of these have polar bonds?
Yes.
No.
It's carbon-carbon bonds or carbon-hydrogen bonds, right? These are all hydrocarbons.
But there's dipoles.
So there could be dipoles, but I'm asking about polar bonds. So no polar bonds and symmetrical. Has to be, so to be inactive, you'd have to have no polar bonds and be symmetrical. So we can look at all these and say none of them have polar bonds, but that doesn't mean they're not IR active yet, right? It's has to be an and, right? So this has no polar bonds. Is it symmetrical? Do you see it being symmetrical?
Yes, it is symmetrical.
It is symmetrical. It is, right? So it's trans, right? So it's, look at it like this. So there's an H here and an H here. So it's almost, right? Everything's kind of canceling itself out, right? Right? 2 carbons pulling, 2 carbons pulling, and H, right? It's very symmetrical about the double bond. Like you could split it in half, and it's kind of like split there. So trans alkenes can be IR inactive because of this, so they won't stretch very strongly. What about this alkyne? Maybe it's a little easier to see, right? Because it's much more linear, right? 2 carbons on either side, so it's going to also be IR inactive, right? It's both these have no polar bonds and they're very symmetrical. But now this alkyne, right? There's an H on one side and then a bunch of carbons. Well, that's not symmetrical, is it? That's not like something you could divide in half. So this would be IR active because it's not symmetrical. Another one you could think about, which maybe is a little tougher. So what if it's a cis alkene? Is that going to be active in the IR? So does it have polar bonds?
No.
No. Is it symmetrical? Think about the double bond, like splitting it in half.
Oh no.
It's not symmetrical, right? The H's pull differently than the 2 carbons on the side. So these cis alkenes usually are always IR active, right? Because it's going to have like a cis and a trans, like a cis side, where one side is much different than the other. And you can have trans alkenes, right? You could easily have a trans alkene
That has polar bonds.
that doesn't have polar bonds, but still, is this one symmetrical?
No.
No, this one's not symmetrical either. So this would be IR active, probably not very strongly IR active, but it'd be IR active, right? So you gotta look for those special ones that are kind of, remember in lab we did the stuff, we counted up the types of hydrogens and carbons? This will help you see that too.
So we don't actually split it like this.
You can split it like this and like this.
But
Or you can split this one like this and it's the same, and split it like this is different.
So you should be able to split it both ways and it's
Yeah.
the same?
Pretty much, yep, good.